I plot as PLT, percentage map plot with inline. So import IO percentage CD and we import data sets. So, so the data is about traffic passing through a junction. You know, traffic CC cameras will be there, right? So the CC camera is counting the vehicles that are passing through the junction. That is the data which we got here, which is the how many vehicles are passing through that particular junction. That is what this data is all about. Let's see, here is the traffic. So this data is all about traffic data dot head. So if you see the time, every 5 minutes, it is counting how many vehicles are passing through that traffic junction. Every 5 minutes, how many vehicles are passing through that particular traffic junction. So it is counting, and also the average speed of the vehicles, average measured time, and median measured time, how much time it took for measuring the count of vehicles. So this is a data collected by CC camera, traffic camera on a traffic junction using a sensor. It is getting the data. There is no manual intervention here. It is collected by the sensor within the traffic CC camera, and it is the sensor is set for 5 minutes time interval. The time interval, if you see the timestamp here, very clearly 11:30, 11:35, 11:40. So every sensor will have a time interval based on which it will, we call it as checkpoint. A time checkpoint will be there. At that checkpoint, it will count. Because if you don't give a checkpoint or a time interval, it will don't know how many. So if you have to set a time interval. So here we have set a time interval of 5 minutes. So every 5 minutes data is stored. So every 5 minutes the data is collected and stored. Once all of you have imported the data, please confirm. Good morning. Yeah, we'll do that explanation. We'll do. First, import the data. All of you import the data. Okay, while you're importing the data, IoT data. What is IoT? Is time series data. What is IoT? Internet of Things. Internet of Things, where data will be captured through sensors, not through human beings, is time series data. A date variable or column will be there in data. Date with time is must. Date with time is must for time series data. Date with time. So basically, we use the word called timestamp. Timestamp means date with time. Now the time can be hours, minutes, seconds. Sometimes you have more than that also. Microseconds, nanoseconds also will be there. Now the timestamp will be having a fixed frequency. A fixed frequency like 5 minutes, 60 minutes, 5 minutes, 60 minutes, day, week, month, etc. So a timestamp will be as small as 5 minutes, or not even 5 minutes, it will be 1 minute also. I have seen timestamps with 1 minute also. So you will have very, very small time within the day. Within the day, 1 minute timestamp also we have seen for particularly web traffic. For a particular site will be measured in per minute for big websites. For big websites like Facebook, LinkedIn, they will measure it per minute. Every minute, they will see how many subscribers are logging in. So Internet of Things is data is a time series data. IoT data is the data collected using sensors, no human intervention or no manual intervention. Within the time series data, you will have a date and time variable. We call it as timestamp with a fixed time interval. That is what we have to, that is the most important thing in time series, the timestamp. Particularly in normal data, we ignore date and time, we extract data and we delete it. But here, time is a very important variable. Now, if you are looking at time series analysis, there are two types of time series analysis: univariate time series, and you have multivariate time series. We have panel data analysis. These are the predominantly used time series analysis. Now, univariate time series. We will first work on univariate time series. In univariate time series, there will be date or timestamp and a variable y. So in univariate time series, there will be only two columns. There will be date or timestamp and variable y. For multivariate time series, variables are extracted from date or timestamp like weekday, month, quarter, etc. So in multivariate, we will extract these variables and other independent variables will also be there. So we will predominantly work on these two types of time series. In industry, we work on univariate time series and we will work on multivariate time series. So participants got it? All right, participants, all of you got this? Can we move forward? Guys, can I move forward?
Yes, sir.
Sir, can you scroll up, sir? Data importing.
Okay. Windows laptop double quotes, %CD double quotes and the path. Windows laptop, %CD double quotes and the path.
Sir, continue.
Yeah. Now we will first create univariate time series. Univariate time series. Traffic is equal to traffic data double square bracket single quote timestamp all caps the column timestamp single quote V capital vehicle count. C capital vehicle count. Traffic dot head. So we have created a univariate time series where we have the first column called timestamp or date with time, and then the variable y, which is the vehicle count. Once you're done, please confirm. Okay, can I move forward? Traffic dot D types. Now there is a problem here. What is the problem?
So timestamp is an object.
Yeah, timestamp is being shown as object. The format of timestamp is not correct. Most of the times, the timestamp will not be read as date time format. We have to manually convert it. Most of the time, we have to manually convert it. In sensors, it will be Unix timestamp. The 16-digit number or a 19-digit number will be there. We have to manually convert it into date and timestamp. Here, our date and timestamp is date and time with a frequency of 5 minutes. Okay. Now let us convert. We need to convert timestamp into date time ns format. Ns means nanoseconds. So this is the default format for date time in Python. Date time ns. Now traffic dot timestamp is equal to pd dot to underscore date time. There is a very interesting function called pd dot to underscore date time. Traffic dot timestamp comma errors is equal to course. Errors is equal to course. What errors is equal to course will do is will replace, if it is not able to read any timestamp, it will replace it into NA. It will replace it with NA. Okay, so errors is equal to coerce. Whenever it is not able to read the date time format, it will replace that date time format with NA. Now, if I run the previous command again, now you can see the date has been converted into date time format. So pd dot to underscore date time is a function that is used to convert date to from object type to date time. Now let us see what happened. Traffic dot head. Now it has the date time has been corrected. Now we have the date with time.
So is there any format that the date has to be for period or datetime converted into a datetime?
PD.datetime is an automated function. It will read any type of data, or you can give the format. Whatever your existing date format is there, that can be given.
Mhm.
So, see, by default in all softwares, YYY so underscore date time. So, see here, there are sub arguments based on your if day is first, you have to give it as true. If year is first, you have to give it as true. You have this thing, right? Month will be always in middle, right?
Yes, sir. Yeah.
So this is how it has to be there. So there are multiple formats it will read. By default is YYY hyphen or slash MM slash DD.
DD,
So
yeah.
by default, the date format is default date format in Python is YYY hyphen mm hyphen dd or same thing YYY slash mm slash dd. Excel also has the same format, right? The other things also. Let me put it the other HH colon mm colon ss. Hours, minutes, and seconds. So this date time function is very important. To underscore date time is now fully automated. It reads the date time automatically. If it is not there, you can give your format also.
So like, for example, instead of a month in numbers, if you have it in string like June or July, would it still convert it into a time?
That's what. No, we had it in string only, right? Object.
But still, it was a number, right? The month was a number like 02 or something. Instead of 02, there
You
was
are saying about month in number name, right?
name, yeah, name.
Yeah, M. Then it is capital M. It will read it as capital M. Small m means numerical month. Capital M means capital single M means short form, 3-letter. JN like that. Two
Okay.
M's means full name.
Okay. Okay.
Capital M. Okay.
Okay. So it would even read that data and
yeah, it will also read that also. So we can see
Okay.
here in the date format, there is a format. Let us say you're talking about month related thing, right? So your format is equal to, see here, you can specify the format here. What is your existing format? Okay.
Okay. Okay.
That you can specify in double quotes. So if your format is like this 10, 11, 22, this is month first, day and year, right?
Yeah.
So that way you can do. Now you're asking for the name of the month, right? So the name of the month, percentage D, percentage M, percentage Y, percentage capital M, percentage capital M will be there, na? That will be reading the text data, text month.
Okay, sir.
Okay. So there are a lot of arguments. You can check it here. 2 time delta series month 2 3. This is your Unix timestamp. I told you now. Actually, when you get the data from a sensor, you will not have the date. It will be like this. You can see here, right? 3, 6, 9, 12, 15. You will have this timestamp. We call it as Unix timestamp. This is 1, 2, 3, 4, 5, 10 digit, right? 10 digit, you'll get it second. Nanoseconds is, I think, 10 plus 13, 16, 19 is nanoseconds. So
Okay.
Unix timestamp. This is the actual date you will get when you collect data from sensor. Now, what happens if you are asking for month name? So month name should also be there somewhere here. Month name, I think it's not there here. I think percentage capital M will read it. Percentage capital M will read the month also. So that should not be a problem. We'll try to do an example, okay?
Okay, sir. Sure.
Yeah. Okay, all of you are done till this point, participants? Can I move forward, guys? Okay, can I move forward, guys? Participants, can you confirm?
Yes, sir.
Okay. Now, our date is in 5-minute time interval. 5 minutes is the time interval. You can see the timestamp here. 5 minutes is a very, very short time interval. 5 minutes is a very, very short time interval. So we need to resample the data. We have to resample the time frequency. We can resample the time frequency into hourly traffic. Hourly traffic is equal to traffic dot resample 60min. 60min means 1 on is equal to time stamp dot sum. So we will know total number of vehicles passing through every hour. Now you can see the timestamp 11 o'clock, 12 o'clock, 1300, 1400, 1 p.m., 2 p.m. like that. So we are converting the data into hourly traffic. So between 11 to 12, we have 124 vehicles passing through it. Between 12 to 1, we have 92 vehicles passing through it. Resampling of data based into time frequency. So total vehicles, sum total vehicles. Per hour. If you want, you can take average also. If you want, you can take instead of dot sum, you can give dot mean, you can give dot median. But here we are taking dot sum. Daily traffic is equal to traffic dot resample small d comma on is equal to time stamp dot sum. Daily traffic dot head. You can see day wise traffic. All right. So if you want to convert it into monthly traffic is equal to traffic dot resample small n comma on is equal to timestamp dot sum. Monthly traffic dot head. You have every month. February, March, April, May, June. So you can see the vehicles every month. All right. Can I move forward? So time series visualization is done using line plot. We use line plots for doing time series visualization. Hourly traffic dot plot kind is equal to line. You can see the plot of hourly traffic. You want, you can plt dot figure Its size is equal to 20 comma 10. Oh, sorry, 10 comma 30. So you can do monthly, the line plots are used for visualization. Similarly, monthly traffic dot plot, sorry, daily traffic. Kind is equal to line. You can see the daily traffic. Okay. So monthly traffic also dot plot kind is equal to line. All right. Now let us look at the univariate time series analysis. Univariate time series analysis can be done only when the data is stationary. Univariate time series analysis can be done only when the data is stationary. Stationary means constant mean, constant variance, and constant auto correlation. Constant mean, constant variance, and constant auto correlation. So stationarity of the data is the primary assumption of univariate time series analysis. The data must be in stationary format for doing any univariate time series analysis. Stationary means constant mean, constant variance, and constant auto correlations. When I say constant means, it does not, stationary time series data do not depend on time at which the series is observed. So time dependency will not be there. That is the what stationary means. Time dependency will not be there. So that is what we need to have. The time dependency, the properties do not depend on time. The data property does not depend on time. That is the definition of stationary. So if you are looking at what do you mean by stationary of time series, stationary. So the red ones are non-stationary. That means time is playing a role on this data. Time dependent mean time dependent variance. This is non-stationary data, the red one. The green one is stationary time series where time does not play a impact or time does not have a impact. So the principles of stationary is very, very important. Now you will also get a doubt, what is autocorrelation? Autocorrelation is correlation between y and lagged values of y. Y and lagged values of y, we call it as autocorrelation. Let us say y is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Lag 1 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Lag 2 means we start from here 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is the lags of y. And the correlation between y and lags of y, we call it as autocorrelation. We call it as autocorrelation. So the data must be brought to stationary. Data must be either stationary or brought to stationary using differentiation. So we have to either the data must be already in a stationary format or we have to bring the data to stationary. That is the format, but the data must be in stationary. Otherwise, you cannot do time series analysis. All right, can I move forward? So we will use daily traffic dot plot kind is equal to line. Now, is our data stationary? So based on this, we are not able to decide whether our data is, I don't think our data is stationary. So if you are not able to make up your mind by seeing the visualization, whether the data is stationary or not, we have certain tests to do it. The first one is augmented Dickey Fuller test of stationarity. This is a very popular test we do for finding whether the data is stationary or not. The null hypothesis is unit root present or data is not stationary. Alternate hypothesis is no unit root or data is stationary. And we will use the same p-value notation. P-value less than 0.05, we will reject the null hypothesis. Similarly, p-value greater than 0.05, we fail to reject the null hypothesis. So the augmented Dickey-Fuller test of stationarity is a very popular test for deciding whether your data is stationary or not when you can't make up your mind through visualization. The null hypothesis is unit root present or data is not stationary. Alternate is no unit root or data is stationary. P-value less than 0.05 is reject null. P-value greater than 0.05 is fail to reject null. Okay. Now, in Python, we have this stats models library. Stats models is a library in Python that helps us to deal with time series data. Stats models is the library that we use for time series analysis. So time series analysis, TSA, we have a lot of methods and all in stats models. So this is the library, which is sub-library of NumPy, which is the sub-library of NumPy. So in stats model, AD Fuller, we have the AD Fuller test here. Augmented Dickey-Fuller test for a unit root. Now here only we will get the null and alternate also. You can see the null hypothesis and alternate hypothesis also. See, the null hypothesis is there is a unit root or data is not stationary. No unit root, data is stationary. And you can see it returns the ADF, and the second value which you get is the p-value. The second value which we get is the p-value. So from stats models dot TSA, dot stat tools import AD Fuller. AD Fuller daily traffic. And you can see the p-value. Since p-value is greater than 0.05, we fail to reject null. We fail to reject null. All right, can I move forward? So to bring data to stationary, discrete differentiation must be done. Daily traffic diff is equal to daily traffic dot diff. Daily traffic diff is equal to daily traffic diff dot drop NA. Because the first observation will be NA, we have to drop it. Daily traffic diff dot plot kind is equal to line. Now this is our difference data. It looks like stationary. Now we have to reconduct the test to confirm whether our data is stationary or not. AD Fuller, daily traffic, diff. Now you can see here the p-value is less than 0.05, we reject the null. So our difference data is what we call stationary. So from now onwards, we have to use difference data.
Sir,
Yeah,
from the p-value only we can decide it is stationary or not.
yeah, based on the p-value. See, what is the null and alternate hypothesis? Null is data is not stationary, right?
Yes, yes.
So we are rejecting the statement here, okay? And you can see here, without doing the differencing, our data is not stationary. But once we have done the differentiation, our data structure has changed and now the data is stationary. The test is also saying data is stationary. All right, all of you are done till this point. All right, can I move forward, participants? The next step is decompose time series into elements like trend. You have an uptrend, you have a downtrend, you will have a neutral trend. Seasonality, the 4 seasons, then residual or error or random. Actual value minus predicted value. Decomposing of time series into 3 components: trend component, seasonality component, and the random or the residual component. Decomposition or breaking the time series into components: trend, seasonality, or residual. There are 3 methods. Actually, there are 2 methods developed by 2 statisticians called Holt-Winters. Holt-Winters method of decomposition. Holt-Winters method of decomposition. They have proposed additive method, which is YT. Guys, 1 second. All right, YT is equal to trend T plus seasonality T plus error T. He also published a multiplicative model, which is YT is equal to trend T into seasonality T into error T. So the additive method must be used for non-seasonal data and multiplicative method for seasonal data. All right. From stats models dot TSA dot seasonal import seasonal underscore decompose. Seasonal underscore decompose daily traffic diff dot plot. You will get the decomposition plot. All right, can I move forward, participants?
So why do we have two sets of similar
Actually, that is
plots?
coming two sets of plots, but one is repeating. I don't know why it comes. We get the
Okay.
two sets of plots, but both of them are same, no difference.
Yeah, the same.
Yeah, it is repeating. There's a problem with the stats model thing. All right, can I move forward?
Yes.
Yeah. So the whole thing is forecasting. Univariate time series forecasting. Based on the time, we need to forecast. That is the purpose of this univariate time series analysis. Univariate time series forecasting, there are many methods. Simple moving average is there, exponential moving average is there, Hart-Winters method is there. There are many methods academically we use in terms of what you call time series forecasting. But the most prominent time series forecasting model is auto-regressive integrated moving average method, also called as ARIMA PDQ. ARIMA method, auto-regressive integrated moving average method. We also have one more for seasonal ARIMA, where we use SARI Max where we will have the normal P comma D comma Q lags, and then we'll have the additional P comma D comma Q, and then we'll also have the frequency. So the popular models which are widely used in industry is univariate time series forecasting. The popular method is ARIMA method, auto regressive integrated moving average, ARIMA PDQ. I will tell you what is this PDQ means, and the seasonal version, seasonal ARIMA or SARIMAX PDQ, and then the seasonal parameters PDQ and the seasonal frequency. We will get the seasonal frequency. Now, if you are looking at ARIMA PDQ, it is three components: AR component, ARP, I is D, integration is the differencing which you have done, and moving average Q. AR is autoregressive, the P parameter, integrator is the D parameter, MA or moving average is the Q parameter. Basically, PDQ are lags that lie between 0, 0, 0, 0 till 5, 2, 5. So generally they lie between 0, 0, 0, 0, 0, 0, 0, 0 till 5, 2, 5. So the values of PDQ, P lies between 0 to 5, D lies between 0 to 2, because we don't go beyond second order differentiation, and Q lies between 0 to 5. Now let us understand each of these components. Auto-regressive, the AR, is linear relationship between values of Y and lagged values of Y. Linear relationship, it's a simple linear relationship between Y and lagged values of Y. The ARP the lag order, like I told you, lies between 0 and 5. And AR terms are positive. AR terms are positive. Then integrated, the I component is the differencing done to bring data to stationary. D lag order lies between 0 and 2. Moving average, or the MA, is the linear relationship between errors and lagged errors. The Q lag order lies between 0 and 5. MA terms are negative. So basically, ARIMA is a linear regression. ARIMA is a multiple linear regression with two equations. Basically, it is with two equations, one AR equation and the MA equation. So if you are looking at ARIMA equation, this is the equation. Yt is equal to intercept or constant plus AR terms lagged values of Y and MA terms lagged values of errors. AR terms are positive, MA terms are negative. These are two are equations, Yt minus 1 till Yt minus P, theta Et minus 1, theta Et minus Q. So here we can see the equation. So it is a simple multiple linear regression equation, the forecasting equation, but with two equations. One is the AR equation, the other is the MA equation. And the Sarima equation. We also need to understand the Sarima equation. So PQ, Sarima is also there, two equations, non-seasonal parameters, seasonal parameters, and the frequency. M is the frequency. All right, all of you got this? And one important thing you need to understand is the missing values is different here. Missing values in univariate time series if you are we have something called forward fill, F fill, which is replace NA with next value. We have backward fill, which is replace NA with previous value. Or you can also do last year same time value. Last year same time value. It can be month, week, quarter, or season. So last year same time value you will use. So any of these, so the missing value imputation is different here. So if you are looking at missing value imputation for time series forecasting, we have to follow these methods: forward fill method, backward fill method, or last year same time frame method. All right, participants. So it's already 11 o'clock. We'll take a break for 15 minutes and come back. Okay.
Okay, sir.
Oh, sorry. Thank you. So the identification of PDQ values or lag order values can be done using two plots: the autocorrelation plot, also called as the ACF plot, which gives us the Q lag. Then we also have the partial autocorrelation plot or the PACF plot, which gives us the P lag. Then we have the differencing, which gives us the D lag. The ACF and PACF plots, when you're looking at the plots, you have to look at the first lag at which there is a significant peak or above blue shade. That will be your lag value. So import plot underscore ACF, comma, plot underscore PACF. Plot underscore ACF, daily traffic diff, comma, lags is equal to 20. Now you can see here, which lag, I think the zero lag only, we can see there's a huge peak. Zero lag only, there's a huge peak. I think the lag value can be 0. So you can see here, then we can also do plot underscore PACF daily traffic diff, comma lags is equal to 20. Here also there's a big change at 0 lag. The peak is at 0 lag. But understanding the lag values from these plots is very difficult. Making sure that we are getting the correct plot values is very, very difficult. So from these plots, we are not able to make what is the value. We cannot decide what is the values of P, D, and Q. Basically, these plots are a little bit confusing. The lag values, getting the correct lag values or the lag order values is a little bit difficult when you're using these plots. So we have these auto ARIMA functions that will help us to find the the best combination of PDQ values. That will be the best. We will get the best value of the PDQ values using this auto ARIMA function. So the auto ARIMA function will try all the values between 0 to 0000 to 525 and will give us the best combination of the values. And based on that, we can finalize our ARIMA model. So the identification of lags through these charts, if you can do it, it's better. If you are not able to do it, it's okay. We can use the auto ARIMA function and then we can come up with the best possible lags. Here, the tentatively, both the charts are showing that 0 lag itself is a very large change, but let us see what the actual auto ARIMA suggests. Now, the interpretation of output. The interpretation of output, the primary metric is Akaika's information criterion or the AIC. Lower the better. There is no fixed value for AIC, but the model that has the lowest AIC will be the better, best fit model. And we also need to check the p values of the AR and MA lags must be less than 0.05. The AR MA lag p values must be less than 0.05. And the diagnostics is root mean square error. Root mean square error. Mean square error. Mean absolute error. So there are many diagnostics, but the primary diagnostic is RMSE. So the primary diagnostic is RMSE, MSE, MAE, mean absolute percent error, also called as MAP. So these are prominent metrics which we look for when you are looking at the diagnostics. All right. So we will be using the auto ARIMA function which will try all combinations of PDQ values from 0, 0, 0 till 5, 2, 5. And the PDQ lag order that has the lowest AIC is the final model. The final model will be the lag order which has the lowest AIC. All right, participants, all of you are till this point. All right, participants, should I move forward?
Yes, sir.
So all of you install exclamation pip install PMD ARIMA. Exclamation pip install PMD ARIMA. All right, all of you have installed. Can you guys confirm? Guys, can I move forward? All of you have installed.
Yes, sir.
So from PMD Arima import auto underscore Arima. So traffic Arima is equal to auto Arima open bracket daily traffic def comma start underscore p is equal to 0 comma start underscore q is equal to 0 comma d is equal to 1. We have already done the differencing, so d is equal to 1. Stationary is equal to true comma m or the time period is 7. Okay. Remove m. Let us see the summary. Traffic Arima dot summary. So it is a seasonal, sorry, there is a lag order. Model Sarimax, where is the lag order? Oh, lag order is not there. Okay. 1 second. Daily traffic diff invalid encountered in reciprocal return np dot roots polynomial -1. Okay. Let us give the actual data. Sarimax 202. Arima 202 is what we are getting if we give daily traffic. Why are we getting this error? It was not there earlier. You also getting the runtime error, participants? Guys, you're also getting the runtime error, or I am the only one who is getting it? Earlier, we never got this error. Why we are getting it now? So auto arima is the function arguments. Start if p is equal to 0, comma, start is equal to 0. It says 0, 0, 1. And b is equal to 1. 0, 1, 0, arima. 0, 1, 0 is the model. You can see here model. AIC of 1809. Oh, d is equal to 0. If I give stationary is equal to true, it is not taking any time. So I will give stationary is equal to. Then we are getting a model 310. Arima 310 is the model. So give this arguments. M is equal to 7 is daily data. So we got a Sarimax model. This is the model we are getting. Seasonal model we are getting. And all the p values are less than 0.05. P of z is all less than 0.05. Once you are done, please confirm. Guys, got it, all of you?
Yes, sir.
So this is a summary. All of you got the same summary, right? The model is seasonal ARIMA 310101. 7 is the frequency. AIC is 1717.
So I
And
got
then the
510.
what you got?
Sarima X 510.
You got 510.
Yes, sir.
Oh, what is the AIC you got?
1702.094.
But how come it came 5? But for me, what about the other guys? Did you get the runtime error?
I got the model fit warning, sir, before. Model fit warning when I was running the above query.
Okay. Because see, the auto ARIMA in PMD ARIMA, there will be difference between Mac and Windows. So that thing is slightly will be there, but not that big difference. It will be small difference only. What about other participants? Guys, other guys, you also got the same 310? Okay. So let's continue. The model we got is here. Now, if you look at the model output, you have to look for the model parameters, the AIC, and the p-values of each of the lags. They are all less than 0.05. All the lags p-values are all less than 0.05. Then you will also see two more things: lung box Q 1.62 and probability Q 0.20, Jacobera 1.74, Q-ness kurtosis, heteroscedasticity, and probability of heteroscedasticity, two side is 0. Now in this box, the lung box is very important. The lung box test of for residuals. The lung box test for residuals. The null hypothesis is model does not show lack of fit. Model does not show lack of fit, or model is fine. Alternate hypothesis is model does show lack of fit. So model show lack of fit. So the interpretation is p-value based inference. Or what we call it as, in this case, probability of Q. Since probability of Q is greater than 0.05, we fail to reject null. We fail to reject null. That means we are accepting the null. That means the model is fine. The model is fine. So the model is fine. So this is a good fit model. You can also do traffic arima dot plot underscore diagnostics. You can see the diagnostic plots. See, normal Q and Q plots, most of the observations are on the line. Got it, guys? All of you?
Yes, sir.
Okay. Now the prediction. Traffic predict is equal to PD dot data frame traffic arima dot predict n underscore periods is equal to 30. We are predicting for next 30 days. We are predicting for next 30 days. Index underscore of underscore FC is equal to PD dot date range daily traffic diff dot index square bracket -1 comma periods is equal to 30 comma frequency is equal to daily. Traffic predict dot index is equal to index underscore of underscore FC. So I am predicting it for next 30 days. What will be the daily traffic for next 30 days? PLT dot plot daily traffic diff comma label is equal to training PLT dot plot open bracket traffic predict comma label is equal to forecast PLT dot legend location is equal to upper left PLT dot show. So the forecasted is, this is the forecasted traffic for the next 30 days, the orange color. Got it, guys, all of you?
Yes, sir. So that's the plot that I got. It's a bit
Yeah,
different.
similar, right?
No, so it's a bit above than.
Slightly, because there will be what you call randomization will be there, slightly difference will be there.
Okay. Okay.
So no two models will be same like that.
Okay, sir.
So this is how we do time series forecasting, univariate time series forecasting in Python. Okay, guys, any doubt?
No.
Mailing the files. So I've emailed you both the files. Okay. Any doubts you can ask me, or we'll end the session for today. We'll meet in the next session.
I'm good, sir.
Good. So shall we end the session for today, participants?
Sir, any practice for IoT
Ah.
data?
You want the IoT data for practice, huh?
Yes, sir.
think this is better. Shampoo sales data. It's a textbook data only. Shampoo sales data. This is monthly data. So you can use this one, monthly sales data. Univariate time series, shampoo sales, 36 only. Daily temperatures, 3650. Monthly, you can also use the daily temperature data set, okay? So this is intermediate, control C. V. Data, the columns. Next. Got it?